Hello guys, welcome to JGK Masterclass. Guys, as you can see, this is a part 2 video on retrosynthetic analysis. In this video, we are going to learn some more problems and its solution on disconnection methods and synthesis. This topic is very important for M.Sc students, M.Sc Chemistry students, and all the problems which are taken in this video belongs to your question paper, and you can find the solutions of those problems in this video. So let's start. The very first problem is, you can see, sketch a retrosynthetic scheme for the following target molecule. So a target molecule is given to you. You can see here a carbonyl group is present along with a non-conjugated double bond. So we'll see how to find out the synthesis of this molecule. For that, first we will see the disconnection approach. As you can see, this molecule, you have a carbonyl group. So we can give numbering with respect to this carbonyl 1, 2, and as you have studied already CC disconnection. So in the CC disconnection, you have learned about 1, 1 CC disconnection, 1, 2 CC disconnection. So here we will apply 1, 2 CC disconnection, and as it is CC disconnection, one carbon will get a positive charge and other will get a negative charge. As you can notice here, the carbon 2 can get a negative charge as it is stabilized by carbonyl. So will be acidic proton, and so you can design these two synthons. For that, we will write down the synthetic equivalent. A positive species is going to stabilize by a negative, that is bromine, and a minus species is going to stabilize by positive. You can also write here COOET, which is a positive species. So positive charge you can stabilize by negative, and negative you can stabilize by positive. That is your choice. And so we got the this synthetic equivalent, which will be the starting material for the synthesis of this given target molecule. So let's see how we can synthesize this target molecule. So you have this ester, which is, you can see the carbon of this methylene is very acidic because of the 2 carbonyl present. And so in the presence of base, a proton will be abstracted from here, which is going to be stabilized through resonance. And so this carbon ion will attack on your second starting material. So substitution reaction will take place, followed by the loss of Br, and it will give you this compound, where if you compare this compound with your target molecule, you have COET extra here. So we just want to remove it. In the presence of base, after doing hydrolysis, you will get your target molecule. So this COET will convert into COH. On heating, the loss of carbon dioxide will give you the desired target molecule. And so with the help of 1,2 CC disconnection, you can find the starting material, and then you can do the synthesis of the target molecule. The next problem, you can see you have a 4-member ring having an oxygen. That is your target molecule. So if we see the disconnection approach to find out the starting material, here you can see here we have CO bond. So we will disconnect that CO bond. Oxygen will get a negative and this carbon will get a positive charge. This is a synthon. And as we have learned in retrosynthesis, positive charge is stabilized by negative species and negative with positive. So for O minus you can write OH, and for positive you can write any negative species. Here we are writing bromine. So this will be the synthetic equivalent for your given target molecule. And in the presence of base, we know it abstracts the acidic proton. The proton will be abstracted, followed by the generation of carbon ion, which will attack on the carbon where the releasing group is attached, and you will get the 4-membered ring. That is your target molecule. You can also design this target molecule like 2+2 photochemical reaction. The next problem, here again you have to find out the disconnection approach for the given target molecule. You can see here the 2 OH are 1,3 position to each other. So we'll see the disconnection approach. First we will convert this OH into carbonyl group. So we will be applying FGI, that is functional group interconversion. So what process we will be doing on your next molecule, that you are designing a carbonyl here, means or carbonyl on reduction will give you OH, right? So whatever you write below the retrosynthetic arrow, that is a reverse process, like when you are synthesizing on carbon molecule, you will be using the reducing agent which will reduce into OH, and so you will get your target molecule. So that is functional group interconversion. And why we are doing it? So that you can apply 1,3 disconnection method, as we have learned already about it, 1,3 disconnection. And in 1,3 disconnection, the two functional groups are placed 1,3 to each other, and you break 2,3 bond. The bond between 2 and 3 carbon is broken here. So if you do so, you will get again one positive, one negative. These are the synthons. Negative we have given here because it is stabilized by carbonyl resonance, and so we can write the synthetic equivalent. Here this hydrogen will give its electron to this, getting a carbonyl bond, and here again minus with stabilized by H plus, and you'll get another molecule of acetone. So 2 molecules of acetone, that is a starting material for the given target molecule. We'll see the synthesis. So first, acetone in the presence of base, abstraction of a proton followed by the nucleophilic attack on the carbonyl carbon will give you 1,3 hydroxy carbonyl compound, which in the presence of reducing agent will reduce into OH, the carbonyl group, and will give you a target molecule. So this is how, with the help of 1,3 disconnection and FGI, you can get the starting material, and then it is a aldol condensation reaction followed by the reduction. You can get your target molecule. The next problem, here again 2 molecules have been given to you, and you have to find out the retrosynthetic scheme. So for that, first we'll see the disconnection approach. This molecule, you can see you have NH2 group. So first we'll convert it into NO2 by applying FGI. And why we are doing it? Because we want to apply now C11 disconnection. So you can see this nitro group is attached to the carbon 1, followed by the C bond breakage. One carbon will get a positive, other will get a negative charge here. So these are the synthons, and you can stabilize it by respective species. So you'll get one is benzyl halide, and the other is, you can get the derivative of nitromethane. And so these are the starting material you can see for the synthesis of the target molecule. So here nitromethane in the presence of base, abstraction of a proton will be there, which will attack on your other equivalent starting material and will give you the NO2 substituted molecule, which on reduction will give you your target molecule. So it's very simple synthesis. With the help of 1,1-cc disconnection and FGI, you can get the starting material and synthesize your target molecule. The next molecule is given where you can see ester, you have ether, and you have nitro group on the aromatic molecule. So here when you have ester group, we'll do first CO ester bond cleavage, and so you will be having here, you can see this carbonyl carbon is positive, will be stabilized by negative species, that is OH, and so you will be having this species, and the other O minus will get a stabilization by hydrogen, which is a positive species, and you will get these two synthetic equivalent. Later again you have O alkylated, so we'll do the CO ether bond cleavage, and you can write down the synthetic equivalent for this. O minus will get stabilized by H positive, and here again this alkyl part will get a positive charge, so it is stabilized by bromine, and these are the two synthetic equivalent. Further, you can do the CN bond cleavage here, the nitro bond cleavage, and you will get here C double bond OH. So this you can treat it as a starting material. You can further do the fragmentation, but we'll be using this to synthesize your target molecule. So you can apply the nitration reaction on this, OH being electron donating, and ortho para directing group, para position is occupied, you will get nitro group at ortho position. So you got this. You can notice disconnection approach is a mental approach, and whatever step we have pursued while synthesizing, we will go in just reverse direction. So here again, we'll be going back in the reverse direction. First step we have done the nitration part. Then you can notice here you have two acidic proton. If you want to have a reaction on oxygen OH, then we have to protect the acidic OH, because acidic OH is more protective, more reactive. Therefore, the reaction will occur on acidic proton, acidic oxygen rather than the phenolic oxygen. So we will first protect this COOH group in the presence of trimethylsilane, TMS. So protection will be there. Once it is protected, then this OH is free to react with your alkylating agent in the presence of base, and you can do the O alkylation. And once the reaction is completed, you can deprotect it in the presence of ethanol and get back your COOH. Once it is released, you can treat it in the presence of base with the other alkylating agent, and you can get your target molecule. And this is how you can design your target molecule with the help of protection and deprotection in the presence of more functional group. The next problem you can notice here, we have two target molecules given, and they have given you CC disconnection you have to use here to synthesize these two molecules. So we'll be seeing first disconnection approach for first target molecule. So this is the aromatic compound. First we'll be doing the cleavage on the bond where you have CC bond cleavage, or this is CC bond cleavage, not CO. You can rectify it. First this bond we are going to cleave, and then later you can cleave the other alkyl part. So you will be getting, finally these are the starting material to design your target molecule. So you can notice how we can synthesize. So basically it is nothing but a famous Friedel-Crafts alkylation reaction. First step, you have benzene and you have alkyl halide. In the presence of AlCl3, alkylation will take place, followed by acylation. Since this group is orthopara directing, at para position you will get your target molecule. The next molecule which is given here, you can notice that you have alpha beta unsaturated molecule, and whenever you have alpha beta unsaturated, you can apply alpha beta cleavage. And when you have beta carbon, at beta carbon you can put a carbonyl group. So you can notice we have done this alpha beta cleavage, and at beta carbon we have placed a beta carbonyl group, a carbonyl group. Now if you notice the two carbonyl are 1, 5 to each other position, 1, 2, 3, 4, 5. So we can apply actually 1,5 disconnection method. In that, when you apply it, the bond is going to cleave is between 3 and 4. So if you give numbering from here 1, 2, 3, 4, 5, the 3, 4 we will prefer on the branch side, rather giving the number from this side we will prefer, so that you can have the Michael type of addition reaction here. So it is, remember, mental approach. We will always prefer the one which gives you more reliable method. And so once you fragment it, you can design here alpha beta unsaturated. So whenever you are doing 1,5 disconnection, you can have one synthetic equivalent as alpha beta unsaturated, and the other you can write down the stabilized by the positive hydrogen, and you got two synthetic equivalent. So you can use these two as a starting material and synthesize your target molecule. But I will tell you, you can also synthesize this molecule by you having a 1,3 disconnection approach. You can see the two carbonyl are 1, 3 to each other. If you notice 1, 2, 3, and when you have 1,3 disconnection, the bond between 2 and 3 is broken as per the rule. So if you break this, you can have one carbon as a positive and one carbon as a negative. So the carbon number 2, we will have a negative because it will stabilize by carbonyl. So you can stabilize by H plus, and so you can write this structure. This carbonyl will get a positive charge, and so you can stabilize by negative species. So we are writing here OET as a negative. So this will be your synthetic equivalent to design your this particular molecule. Now here again, if you notice, the two carbonyl are 1,5 to each other, and when you have like this, you can have breakage between 3 and 4 carbon. So you can apply 1,5 disconnection approach, and when we have 1,5 disconnection, one of the synthetic equivalent will be alpha beta unsaturated, and the other will get negative charge. You can stabilize by positive species. So positive we are writing here COET. So you will get like malonic ester type of synthetic equivalent. So these two will be the synthetic equivalent to design your molecule. So we'll see how to synthesize your target molecule. So basically, if you notice, the reaction is Michael addition reaction followed by the Robinson annulation reaction. So now we have the carbonyl compound here, the malonic ester, in the presence of base. This methylenic carbon proton is acidic because it is having two carbonyl group, so that this carbon ion going to have a resonance between the two carbonyl, and it is going to be a stabilized carbon ion, and so we say it is an acidic proton. Followed by, you can see alpha beta, this unsaturated carbonyl. So Michael addition will takes place, and after hydrolysis on heating, you will get this molecule here, where the COET will be converted into COH, followed by the loss of CO2. You will get this molecule, and then in the presence of base, acidic proton will be abstracted, and followed by the intramolecular aldol condensation reaction. You will get a next molecule which will react with again Michael addition reaction. In the presence of base, acidic proton will be abstracted, and you will get the molecule where again in the presence of base you can show intramolecular aldol condensation reaction, which on heating will give you alpha beta unsaturated carbonyl compound, and that is your target molecule. So if you can notice, in this full synthesis, we are using three major reactions: aldol condensation, Michael addition, and Robinson annulation reaction. So whenever you want to design a ring, you can use Robinson annulation reaction, and before Robinson we can have Michael addition, and Michael addition we have one of the synthetic equivalent or starting material as alpha beta unsaturated carbonyl compound, and so you can design this target molecule. Next problem, you can see again we have two molecules here. They are asking you CC disconnection. So we'll see the first molecule having a CC disconnection. We are doing here 1,1 CC disconnection. So in that case, we'll be getting here one synthons. One will have a positive charge. Carboxylic carbon we are giving here negative charge. Usually carbon will have a positive because it is having oxygen. But here we are writing negative, means you can have it as a unpolar synthon. So you can stabilize by any positive species, or you can have a unpolar reagent, that is Cn minus, which will be the synthetic equivalent for your acidic COH group. And here positive carbon is stabilized by negative species, so you have here Br. So we'll see these two are the synthetic equivalent to design a target molecule. Now you can take sodium cyanide, where the substitution reaction will take place with the loss of sodium bromide. You will get Cn substituted molecule, which on hydrolysis in the presence of base will give you your target molecule. And so with the help of reversal of polarity, you can see here carbonyl carbon here is having a negative charge, so which is unusual, that is unpolar reagent. Next molecule we'll see, you have a long alkylated carbonyl compound. So if you have only carbonyl functional group, we'll do numbering 1 and 2, and with respect to that we will do 1,2 CC disconnection. you will get synthons. Carbonyl carbon is getting a negative charge here, so it means here this is a unpolar synthon. Reversal of polarity, you can notice normally we have seen we have oxygen and this carbon will get a positive charge, but you can notice here we have written here minus charge and the other carbon is positive, so you can stabilize it by negative species. This negative charge means you will stabilize or you can write down any suitable synthetic equivalent for that. So as we know, acetylene will be the synthetic equivalent for it, where you will get a carbon with a negative charge. So whenever you have this CO, you can write here actually one sigma bond also, this carbon bond. Since we are fragmenting it, the carbon 2 will get a negative charge. Here one bond should be there, so which will get a negative charge. And so you can write down this as synthetic equivalent with the C5H11Br, and these are the two starting material to design your starting target molecule. So you have acetylide here. The substitution reaction will take place with the loss of lithium bromide, will give you acetylene derivative, which on oxidation or hydrolysis will give you here CO. So basically this conversion we have learned in how, like whenever you have COCH3 or COCH2 here, you can convert it into acetylene, right? So this is how you can design your target molecule with the help of conversion into acetylene or acetylide. The next problem here, again they are asking you to synthesize these two molecules with the readily available material. We'll be seeing the first synthesis, that is Dienes, and for that we will find out first disconnection method. So when you want to design the Dienes, first is we'll apply FGI, and in FGI means we are doing dehydration here, means dehydration of this molecule will give you a double bond, right? So on the retrosynthetic arrow, whatever we write here, it is just a reverse process. So when you have synthesis, you have this molecule which on dehydration will give you a double bond. So you got this molecule OH, and then we are again having FGI, and FGI we are converting into, you can see here having acetylene, means on acetylene you are having reduction reaction, you are converting into alkene while synthesizing. So this is the familiar structure we have learned in the rule that you have here. You can apply 1,1-CC disconnection method. This is the carbon one which is having a functional group as well as a carbon-carbon bond which is going to be broken. So you can have here carbonyl. So this is actually 6-membered ring. You can write here 6-membered ring carbonyl compound. 6 carbons are there along with acetylene. And so you can synthesize this, again you can write down 6-member. In the presence of acetylene and base, you are having here the first acetylene will form an acetylide. The acetylide will attack on the carbonyl carbon and will give you after hydrolysis OH and acetylene, which in the presence of hydrogen and Lindner's catalyst, which converts into cis alkene. The alkyne will be reduced to cis alkene, and after this you can have dehydration in the presence of KHSO4, which will release the water and give you the diene. So this is how you can synthesize dienes with the help of dehydration and reduction 1,1-CC disconnection approaches, you can see, and reverse phenomena you can apply. Notice I have written here 5-membered ring. The same you can apply because the target molecule is given 6-membered ring. So actually you just write it down for 6-membered ring. This has to be 6-membered ring. The next molecule which is present here having only one functional group, carboxylic COH. So we can apply 1,2-CC disconnection. So here again carbon-carbon disconnection, one carbon will get a positive, stabilized by negative species. Other will get a negative, so stabilized by positive species, that is hydrogen. So this is a malonic ester, and you have alkyl halide synthetic equivalents. You can use these two to synthesize your target molecule. So in the presence of a base, abstraction of acidic proton followed by the substitution reaction or alkylation you'll get this molecule. And if you compare the two, your target molecule, you have one COOH, so that you can get it easily. Base hydrolysis and followed by H plus and heating, you will get your target molecule. And this is how you can design your target molecule having 1,2-CC disconnection. This is the last problem where we have to find out or we have to design this molecule using this as a starting material. So you have an ester functional group. How to convert this ester into this alcohol part having 2-methyl group. So we know we can use here Grignard reagent. Since you are having here 2-methyl groups, we can have methyl magnesium bromide as a nucleophile here, which will attack on the carbonyl carbon followed by the loss of OCH3. You will get diketone. Again, the second molecule of Grignard reagent, and after hydrolysis, you will get your final product. So this is how, with help of Grignard reagent, you can design your given product or molecule. I hope the video will be very helpful for you to solve your M.Sc Chemistry problems. You can solve and collect many more problems and apply such kind of strategies which we have learned today. Happy learning.